If we have two plates, each with area A, one carrying a total charge of plus Q, the other charge of negative Q, then the charge distribution on the positive plate is Q over A, so the electric field is 2 pi K sigma. Sigma is just Q divided by A again, and we have the electric field's 2 pi K times Q over A. The negative plate has an electric field that's going to be negative 2 pi K Q over A. All this means is that the field from the positive plate will be directed away from the plate, and the field, the negative plate, will be directed toward the plate. These fields don't fall off as distance except near the edges of the plate, where the symmetry argument doesn't hold. The result is that the electric fields reinforce each other between the plates and cancel each other outside the plates, again except for a very small contribution around the edges. Now, if the plates are separated by distance d, the situation is between the plates we have electric field 4 pi K Q over A. And what we want to do is determine the potential difference between this plate and this plate. That is, potential difference AB from point A here to point B here. That potential difference has a magnitude that's just equal to the work done between A and B divided by QT, which is the F delta S divided by a test charge. F being the force on a test charge is going to be QT times the electric field times D over the delta S, of course, is just the distance D between the plates, so that what we end up with when we simplify this is just 4 pi K times QD over A. And this is the voltage between the plates. And actually I've been a little careless with my signs and with the forces. This should really be the voltage from B to A, because if we go from B to A, then we experience the positive, well, we experience the force in this direction, which means we have to exert a force in this direction. If this is the force being exerted, it would actually be negative if we went from A to B. I'm not going to make that change, but that's something we do have to be a little bit careful of. And you see where I made an error here. The capacitance of a capacitor is charge over voltage. If we divide the charge by the voltage that we just calculated, we cancel things out and we get the capacitance as 1 over 4 pi K times A over D. Now remember that 1 over 4 pi K is your epsilon naught, and when you get into capacitors, epsilon naught is your convenient notation. However, I'm maintaining the K, and this will be the expression that I'm going to use for the capacitance. Telling us that we have a large capacitance, we have a large area, and a small d. Capacitance means a large capacitance means we can store a lot of charge for a given voltage. If we have a large area, then the charge is spread out over a larger area. We have a smaller electric field, which is going to give us a smaller voltage, which is advantageous if we're trying to store a lot of charge with a little bit of voltage. If d is small, then we don't have a lot of distance between the plates, and the work done between the plates, the F delta S between the plates, is going to be small. And again, the voltage is going to be small. So small d gives us a large charge to voltage ratio, and a large A gives us a large charge to voltage ratio.